right, let's get back into chapter 14 on ethers. Okay, we got a little bit into this last time. Let's get more into it today. So we want to learn how to name ethers. So let's draw a few ethers here. See if we can name these three to get started. Okay, let's just focus on this one first. Okay, so remember we named both sides of the oxygen, so we have a methyl and an isopropyl. Okay, so we'll just write them in alphabetical order. Get isopropyl methyl ether. But what about this next one? I can name this side as a methyl, but what in the world do I name that side? Can't really do it. So for this one, what we're going to do is make this here our parent chain. So we got a pentane, okay? And so on the third carbon, we need to call this thing something. That's called a methoxy group. So we have 3 methoxy pentane, okay? So methoxy, or 2 carbons, ethoxy, propoxy, butoxy, and so on. Okay? What do you think the name of this one here would be?
Trans.
Okay? So it doesn't matter how you number it, let's just number it like this. So we have trans 1, this is a ethoxy, and on number 2, that's a methoxy, and then finally you have cyclohexane. Okay, so a pretty long name, but now it should be pretty easy to name. Okay, any questions on those 3? Okay, so if you can name those 3, you can handle any ether that comes your way. Okay, let's look at some more ethers. And these we'll call cyclic ethers. Okay. So let's look at a series of cyclic ethers. Simplest one is a 3-membered ring. Okay, and these have some names that you just have to memorize. Okay, this is what's called oxirane, strange name. sometimes you'll hear it called ethylene oxide. That's what you'd hear it called when you went to an industrial plant. You could have a 4-membered ring. It's called oxetane. So you have oxarane and oxetane. When you get to the 5-membered ring, okay, the naming for this 5-membered ring actually comes from this one here that has 2 double bonds in it. This molecule is what's called furan. Okay. We'll study that one more in 242. But if you hydrogenated that with a total of 4 hydrogens, that gives us this saturated one that would be called tetrahydrofuran, or if you see it there, tetrahydrogen, 4 hydrogens added to furan. Okay? This is sometimes just abbreviated as THF. Okay. And lastly, we could look at a 6-membered ring. The 6-membered ring, in like way, comes from the unsaturated case, such as in furan, but this is not called furan, this is called pyran. And so if you hydrogenated pyran, you would get this. What do you think that's going to be called? Tetrahydropyran. Or oftentimes THP. Okay, so these 4 here in this square are very common names, especially when you get into biochemistry. Okay, those of you that are biology majors, have you studied the sugars yet? Like glucose? Okay, well, one class of sugars are what are called the furanoses, which are 5-carbon sugars. And you also have pyranoses that are 6-carbon sugars. So your main sugars that you study are either classified as furanoses or pyranoses. Okay? Does anybody know which one glucose would fall under? Is it a 5 or a 6-member? 6. So it would be what, a pyranose. Okay? All right. So I'll let you wait till you get to that in those classes. Okay. Another cyclic ether. You have 2 oxygens in there. That's called 1,4-dioxane. It's a toxic molecule. One of the things about ethers, they have some properties. One of the big things that they are used for are as solvents. So if you do an organic reaction, typically they are done in an ether solvent. Probably the most popular ether solvent is tetrahydrofuran. So if you go to a lab upstairs, you will see a big pot, usually of THF, where they continually are using it. Okay? Another property of ethers is that they are volatile. What does it mean if something is volatile?
Unstable.
Fumes. You smell the fumes, so it's giving off fumes, which means what? It has high vapor pressure. Okay, so the molecules are releasing very easily. It's not staying stuck with the others. So if you ever open up a can of ether, guess what? You can smell it very quickly, okay? Because it's coming to your nostrils very quickly, okay? So it's not a real bad smell, it's just kind of a little pungent smell, okay? And that leads to a third property, is that they are very flammable, okay? Yeah. Okay? These things are very flammable, okay? Not necessarily explosive, okay? If you went up and took a flame to an ether like THF, okay, the thing would not explode, the thing would catch fire. And it's interesting how ethers burn, okay? If you had a little beaker here of ether and you set it aflame, you would see the flames coming up and not necessarily touching the liquid. Why is that?
Is it because the flame, is it because it's hitting the gas?
It's hitting the gas, which is coming off of it. So it's surviving off the gas fumes and not the liquid, okay? So you can keep that in mind as you deal with ethers, okay? Did you ever see an ether truck, a big tanker truck? I've seen ether trucks, and on the back they say volatile, okay? So maybe you saw the same thing. Okay, so that's our introduction to ethers. Let's start looking at the chemistry of them. Okay, so let's look at, first of all, how to make ethers. First way is something called the Williamson ether synthesis. The Williamson ether synthesis, the most popular way to make ethers. Okay? The Williamson ether synthesis uses alcohol to get started. So let's do an example. Let's start with methanol. If you took methanol and reacted with sodium metal, do you remember what you got? It took off the hydrogen. So it made the methoxy ion. Okay? You can carry along the sodium too. So you get sodium methoxide. And remember when we made that was what? A wonderful nucleophile. Okay. So nucleophiles are begging to react with a substrate. So that's what we react next. Remember, substrates have good leaving groups, such as the halogens, such as a tosylate group. Okay? And so here, you'd end up getting dimethyl ether. Okay? That's the Williamson ether synthesis. You take an alcohol, react, create the nucleophile, and react with the substrate to get your ether. Okay? Let me give you some examples and see if you can do this. What I'm going to do is give you the ether. You tell me how to get there. Okay, fill in the blanks. Okay, so if you want to work with a partner, try to figure it out, go right ahead. Figure out what alcohol to start with, and then proceed. Don't be shy. I'll be calling somebody to go up to. Might be somebody in the back.
Right.
That's the first of them is the problem, so it'll probably be cyclo.
Get a key.
Or alcohol of the the OH connected to the CH2. Yeah, then it mixes with CH3BR. O gonna take the CH3. Gonna bring it to I think when bring it up,
Why don't you come on up here? Backward. Come on up. More up. Don't be afraid if you get something wrong. We'll help you. What alcohol did you start with? Okay, so you start with an alcohol. What is that? That's an ether. Okay. Go ahead and give her a little help. Okay, good. So you want to start with an alcohol. So I have an OH. Okay. So good. So we'll react with sodium. Good. Now what will that become? Okay, so that has a minus, and a plus. Okay, good. So we're almost there. So now, what's going to be the substrate here?
CH2, bromine, CH3.
Let her do it. Let her do it. Now, I had a bromine here, so let's put a bromine there. There you go. Good job. Okay. Does anybody do it another way? There's another way to do it. Anybody do it another way?
Yeah, we switch to CH3, so CH2.
You start with the other one being the alcohol. So I could have started with that there. Could have done it that way. You probably did it that way, didn't you? Okay, which would be the better way to do it? Why is it?
Because it's easier.
Okay, because here the substrate is a primary substrate, okay? So I'll have less sterics, okay? So that will be an easier attack than this. This is a secondary substrate, so that will be more difficult, okay? So the first way would be the easier synthesis. The second way, the sterics would not make that as good, okay? You could still do it, but your yield would not be as high.
Like if that was on the test, would you take either or?
Yeah, take either or. Okay.
So the.
All right, let's look at another way to make ethers, which is by way of review. Okay, so the second way is the mercuration reaction. Remember that? What molecule did we start with in this here? What kind of hydrocarbon? Back in chapter 8, alkenes. Okay? So here, remember, we were reacting with mercuric acetate and an alcohol. And then secondly, NaBH4. So everybody remember what that reaction did?
It got over the double bond.
And put an OH.
And put a,
It added this alcohol to the double bond. Which carbon in the double bond got it? The Markovnikov product, the more substituted carbon. Question?
oh, I just wanted to know, like, is it pretty much the same, process as when you do the oxymercuration? So you're gonna add the O, when you, do the mechanism, you're just gonna add the OCH3, or you're gonna drop the H?
That's right. That's exactly it. So you found it perfectly in your notes. Okay? So you get the 2-methoxy butane. Okay, so let me give you one. All right, show me how you would make that one using this synthesis. You got it? Come on up. Okay, I want you to come up and help her. I want you to come up and help her. have a seat. Very good. See? Need to be more confident. Okay, so she saw that ethanol was being added, so I can put the double bond here. Both carbons are equally substituted, so it doesn't matter which one you add to. Question?
No matter which side the double bond on.
No. Cyclohexane, so you can put it anywhere you want. Okay, so let's go into our next set of reactions. This will carry us over into Monday. Here we're going to study what's called ether cleavage. Ether cleavage. What's cleavage? Cleave. Cleave. Okay. So let's look at a real simple one here. What we're going to do is cleave an ether using HBr as an acid. Okay? So we can see we're going to use either HBr or HI. Okay. So let's see if we can follow this reaction. Okay, so remember the hydrogen, partial positive, so you would predict the oxygen to attack, kick off the bromine. So we get that there. So we have a hydrogen that's added to the ether. Remember, sometimes that's called a proton. So here we have a protonated ether. Okay, just like a protonated water was H3O+. Okay. What molecule do you see inside of that protonated ether? You see what? What's the name of that alcohol? Methanol. Methanol. Alcohols, just like water, are wonderful leaving groups. Wonderful leaving groups. Don't forget this. Water and alcohols are wonderful leaving groups. would you predict here the bromine to come
What would it say?
and kick off the methanol? And so the ether is now cleaved. See that? So it's basically the opposite of the Williamson ether synthesis. And now you get the alcohol, and you can go backwards if you wanted to. Okay. Any questions on that? That's our ether cleavage. Now I'll give you one for the end of the day. See if you can draw the mechanism and the products for that one. You get it? Come on up. No, I was calling her.
Me? Oh, she probably did.
Anybody agree with that?
Yeah.
Anybody disagree? Okay. So let me clean it up a little bit here. Okay, that's leaving. Okay, so very good, you get those two there. Now if you look, the iodide could have attacked on that carbon. What's wrong with it going over there?
Nothing.
Sterics. Okay, so here, this is the better attack. Okay, so it'll attack the less substituted carbon. Okay. All right, so we're going to pick up on this on Monday and finish the chapter. We'll see you then.